everyone, and welcome back to another OpenGL stream. It has been a minute since we last wrote any code for OpenGL and making graphics programs. But today I have come back with some original stuff. Today we're going to be we're going to fix the problem that we ran into last time with the textures, with the troll and how the textures were all messed up. And we're also going to look at how to make a mock or simulate an FPS camera where the gun is always attached to the camera, rotations and all that good stuff. So we'll be learning a lot about matrices and vectors in this as well as writing some quality code. So let's go ahead and get started. So let me just Alright, so the first business that we have to do is look at the troll. So last time, before we got into the gun, we looked at the Lord of the Rings troll model. And let me just load it up real quick. And make sure that you set no texture to false, because this relies on textures and not materials. Let me just pull the code up just to make sure I'm doing all this right. Okay. Alright, so when we run this, what we see is that we get this really abominable thing, but it the texture is all messed up because the texture of this moccasin here, or whatever that thing is, not a moccasin, is on the troll. So we obviously messed up in some way, even because we know it loaded it in because it says it right here. So we can actually remove that print statement. I need to figure out where I think we print that stuff out in texture, do we? Model. Yeah, we printed it out in model, okay. So we actually just forgot a single line of code, and it's usually just a single line of code, and that is in the texture class. So in the texture class, when we have our constructor, what we forget to do is actually generate the texture with an ID. So our ID is set to 0, and we don't bind anything to it. So what we have to do is just call generate from the constructor in the texture class. And now when we run this, we should get our expected nude troll. Holy crap, does this guy have tonsils? This is getting kind of creepy. Thank God he doesn't. I mean, now I'm grateful now that he doesn't have a fucking fat cock. But holy, alright, this might be a little much for streaming. I'm sorry about that. But yeah, so that looks a lot better. That lighting looks really good. But yeah. So once again, the moccasin up there, I'm just going to call it a moccasin. We haven't done any skeletal animations yet, so that's not really an option right now. But holy crap, look at the pecs on this guy. He does have a little bit of a beer belly, but look at this just absolute unit. Alright, regardless of that, that's all I wanted to do to fix that problem. Alright, so now let's go back to the gun, and let me just see where we are at. Did I? Oh, I initialized the camera in camera. Where do I initialize camera? Oh, I missed it. Okay. Yeah, so let's just look at this real quick. So what I believe will... Oh, right, the textures, yeah, that's right. So what I believe we did was we actually added a line of code to rotate this. I haven't looked in this in a while. Yeah, we did. Okay. So we're going to go ahead and change a little bit of the camera code, just defaults, just so it looks a little more, so it's easier just to do and rotate. So we're going to set the initial yaw to 0 and the initial camera front to only 1 in the X direction and 0 in the Y and Z direction. This is because that's where the yaw and pitch angles are set to 0. That's camera front, and then also have to update the position to just 0, 0, 0. And let's try this out. Something's wrong there. I probably translated this incorrectly. Oh, yeah, I did this for the troll, that's right. So let me just make this 0 as well. Okay. And there we go. Okay, so we should get that because the gun is in the middle and it's at this whatever angle, and I also do have to set no textures to true, even though it is. But it's not getting on any of the textures. That's weird. And let me try setting this to false. No, that okay. I guess that was right then. I guess it just interpolated it differently. Okay. Anyway, so we're gonna go ahead and we're gonna create a class for this gun object in our models folder, so we can actually sort all the model translating and rotating code into a single file instead of having it in the main file here. So in models, go ahead and create a new file. I'm going to call it gun.hpp. And in here, we're going to go ahead and include model. So /model.h, and then we're going to say class. Hold on, let me just make sure. Yeah, alright, we're all good. So we're gonna say, we're also gonna include the camera because we'll need that. So include /io/camera.h, and then we're gonna do our class now. So class gun inherits from public model. So this is just like the cubes that we have, or that we had. Next, we're just gonna do only public methods. So in the constructor, we're going to have an empty constructor, and we are going to initialize our superclass, the model, with a GLM vec3 position of 0.0f and a size of the 0.05f. So GLM vec3 0.05f, just to scale that down. And then because it doesn't have any textures, we're going to say no text is equal to true. And then we're going to have an empty body there. Alright, now to actually load the model in, since we aren't doing a, we could do this in a method. We could just call gun.loadModel. You know, let's just do that actually. So we'll leave the initialize method empty because we don't actually have any code that's specific to this model. So let's go ahead and in main.cpp, let's include this file. So include graphics/model / gun.hpp. Alright, and then let's go ahead and create the object. So let's replace this with gun g, and then g.loadModel, because that's an inherited method from the model class. And we're going to say assets /models /m4a1 /scene.gltf. Alright, and then in the main loop, we're going to have to render it, so g.render. And then we're going to say g.cleanup at the end instead of m.cleanup. So let's go ahead and actually run this and make sure that it still works. Yep. Alright, so that looks right. And what you will notice is if I don't move the camera at all, by default already looking in the direction of the gun. I don't know why this color is really weird. Like when I was testing this, oh, you know what? No, that's right, because there is, I think I amplified some color, or the difference at least. But I don't know. Okay, so let's get started in the render. So like I said, we're gonna initialize the model matrix, so the local matrix of this of the model, independently of just its position and size, because we do want to add some rotations in it so we can rotate with the camera. So in order to do this, we have to add add something to the model class. So we're going to add a parameter in the render, and it's going to be bool set model, and by default it's going to be set to true. And then in model.cpp, add that parameter. And all we're going to do is, in the render method, we're going to say if set model, we will just go through the code that sets the actual model. And if we set it independently, we're just going to set that parameter to false. And we don't have to change any of the other code because the default is set to true. So by default, we do want it to set the model. But for the this model, we will not be doing that. So you can close out of the model class, and just make sure I'm doing this right. Alright, so now in void render, and we pass in shader. And you know what we'll do? We will actually just add our bool set model in here. Is by default set to false. We'll just say false for now. This is just because if we want this class to like purely inherit from model and like completely override this method, it won't do that if there's no second parameter here. So by setting that second parameter, we allow that overriding. So if we were to say have a list of models, and we called and one of those was a gun like this, then it would call this method instead of the model.render. So that's why we're doing this. Alright, so let's go ahead and do our placeholder. So glm mat for model is equal to our identity matrix. And then we're going to let's scale it first, just because we already know how to do that. So scale, so model is equal to glm scale model, and we're going to do it to size, and that's from the model class. And then we're going to say shader.set map for model, and then we're going to call the model class, so model render, and we're going to pass in the shader and false for set model because we already have. I know I'm saying model a lot, but we're only doing two. We're doing a matrix model, which is in the model view projection model. I keep saying model. In the model view projection algorithm that sets the position, size, and rotation of objects. And then this is the model class that loads in 3D objects. Or just holds a list of meshes. Alright, so like I said, we want to be able to keep this with the camera. So the way we're going to do that is we're going to set position. So position, and that's from the model class that's inherited, we're going to say is equal to camera default camera.camera pose. And then what we can say is model, the matrix this time, is equal to glm translate model and position, just like that. And in doing so, we'll get the exact same result that we have, I hope. Yeah. So you see that I'm pressing the keys. The lighting is changing, but the gun itself isn't. Like, I can rotate around, but the gun itself is staying with the camera. So we do want to be able to see actually, through the sights on a gun in an FPS game. So we're gonna have to offset it by some point. Now we can't just do, it wouldn't be okay just to do the down here. You know, let's just do some experimenting. So from position, we're gonna want to put it down and forward some bit. So down, let's do this. So camera pose, and then we're going to add to this vector. So let's do the forward bit first. So plus glm vec3 of camera default camera dot camera front. So we want to translate it forward times 8.0. So 8 units in the forward direction. So let me actually go into OneNote. Plug in my drawing tablet real quick so I can write this out. So let's say we have our object and it looks like this. I'm trying to do 3D as best as I can, and let's say that our camera is right in here and camera forward is like that. So, and we want to translate it 8 units in the camera forward direction. Now, because the camera forward direction is normalized, we can treat it as its own unit vector. So a unit vector is just, I talked a little bit about this in the vectors video a while back. So it's just like 1 unit in any direction. So in the, let's say in the x direction, the unit vector is called I, and I is usually like 1 meter or 1 second, stuff like that. So we'll call this unit vector f hat, and essentially what we're doing is we want to translate 8 of these f hats in that one direction. So the way we do that is we just say 8 times camera front, which is its own unit vector. And then we also want to go, hold on, just give me half a second. Oh, give me half a second. Alright, I'm back. Yeah, so as I was saying, we're going to translate this 8 units in the forward direction using that as unit vector. So in code, that's how we're going to represent this. And then we're also going to do it down by, I did some experimenting, and 3.15 units seems to be about good for this model specifically. So the way we're going to do that is, let's just do down as just as the negative in camera up. So we're going to say so plus glm vec3 camera default camera dot camera up times negative 3.15 f. And once again, camera up is its own unit vector, so we can do this as well. So let's go ahead and run this and see how it works. Alright, so that actually looks pretty good. So you can see that it is moving with the camera, but it's not rotating at all. It's always pointing in the positive X direction, which is fine because that's what it's set to. But you do see that we do have some sort of rotation abilities with this, so yeah, that's pretty good right there. We may have to change that, and I hope we won't have to, but let's hold off on that for a second. Alright, so that is the setting the position. Now we're going to have to rotate in two directions. So we're going to have to perform two rotations at the same time. The first one is going to have to be the translation of the up and down, so along the X or Z axis, depending on which one. And the way we're going to do that is we're going to find the angle between two of the vectors from the camera, and then we're gonna rotate it by that amount, and we'll see how that works. So let's just go ahead and do a little bit of printing. So if we press the keyboard, or if we press the spacebar, so if keyboard key GLFW key space, and we want to print out some of these values. So we're going to print out the camera up and the camera front. So standard cout, we'll say camera default camera dot camera front dot x, and then we'll do this for the other two components, and then for the camera up as well. And then at the end we'll have a standard end line. And then we want to do camera up. Alright, so let's go ahead and run this and see how it works out. Oh, I got an error. Keyboard. Oh, I need to include it. Yeah, that's right. Include. Not sure why that the compiler wasn't giving me this error. That's weird. Okay, so let's go ahead and just put this over to the right and do that. And alright, so that looks pretty good. Camera up. So camera front is just in the positive X direction, and camera up is the just world up, so one in the Y direction. Now if I look down and to the left around, that's what we get, and camera up is a little different. So let's actually let's get in the positive Z direction and just get some of those values there. I'm still getting... Alright, there we go. That's good. Alright, so let's take these values down. So we have, I'm actually going to put these two vectors in a graph, and we're gonna, oh, this is messing up. Okay, whatever. Alright, so let's say vector 1 is the camera forward, so we have 0.405, 746, negative 0.069, that's a funny number, 7565, and I mistyped it. And then we'll say 0.91132, that's the first vector, which will be the blue. And then the second vector is the camera up, if I'm right, and that's 0.0283725, 0.9976564, and 0.0637257. I mistyped that as well. Alright, so let's draw these, and we see the Z direction is not up in this case, or yeah, the Z direction is up in this case, and Y is not. So just try and visualize it as if it was. So we would be looking at it like this, right? No, we'd be looking at it like this, kind of. I can't even tell. Alright, or no, like that. I can't even tell. Okay. Anyway, that's camera. The blue one is camera front. Let me just make sure of that. Yeah. So the first one is camera front, which is the blue one, and this is camera up, the red one. So the first one we're going to do is we are going to rotate this object around the camera right vector, which will allow us to rotate from camera up to camera front. And then we're going to rotate around the camera up vector by some angle. So let's actually just go ahead and look at a formula. It's called the dot product formula. So let's say we have, let's start with the going side to side. So when you move the mouse side to side, we're changing the yaw of the camera. So we are increasing or decreasing dx. So I can actually just, all right. So we have our initial vector. Let's put the I hat and k hat like that. So x and z. So this is x and this is z. K is just the unit vector in the z direction. So let's say that we have our initial gun vector. So this is the gun, and that is equal to 1, 0, 0. That's just how the model initially looks. And let's say that we are looking at this angle over here. So there's an angle between those two, and this is front. We'll call this G and this F. So the way we're going to do this is, in order to find that angle which will allow us to rotate, and the angle that is perpendicular to both of these is coincidentally camera up, and that's pointing out of the screen with that notation, so camera up. So we're going to rotate it around this screen, around camera up rather, counterclockwise of theta. And how do we find theta? We're going to use something called the dot product. So G dot F is equal to the magnitude of G times the magnitude of F cosine of theta, which is where theta is the degree, as the angle measured between the two vectors. And you might notice that we can actually just replace gun with 1 and 0. And the length, this magnitude is just the length, so square root of the component squared. But the reason, so we're going to do something weird here. We're only going to consider the x and z components. So if this front had some y component, we wouldn't want it to measure the angle between the xz plane and the y component of it, because then that would mismeasure. That would give us a wrong calculation for the horizontal shifting of the angle. And once again, since the horizontal movement of the mouse controls the movement in the xz plane, we're only going to consider the angle in the xz plane. So we're going to replace this with 1, 0. So it's xz dot fx fz. That doesn't look right. And this is equal to, and the length of G is 1 times the square root of fx squared plus fz squared cosine theta. And if we were to solve for theta, what we would get is theta is equal to the dot product. So we're going to say G dot F over the magnitude of G times the magnitude of f, but once again, it's just the magnitude of g is just 1, so it's just going to become g dot f over the magnitude of f. So let's write this out in some code. So GLM actually has a function for us to do this. So we're going to say rotate around, and we're going to say camera up of using dot product. So we're going to say, just to minimize code that we write, I'm going to go ahead and create a new vector called front2D that will measure that will contain the value of the 2D vector of the camera front. So glm vec2 front2D is equal to glm vec2, and we're going to say camera default camera dot camera front dot x and camera default camera dot camera front dot z. Once again, because we're only doing the x and z components. Now we're going to get the angle measure. So make sure that's a vec2. So we're going to say float theta is equal to I messed up with my calculations here. This is actually the cosine of theta is equal to that. So theta is equal to the arc cosines, or the inverse cosine of g dot f over the magnitude of f. So in code, this is going to look like glm dot, that's just a method, and we're going to pass in the two vectors. So glm vec2, and that's 1.0 and 0.0f just for the gun direction, and then front 2D. And then we have to apply our operations to this, so we're going to say a cosine of that dot product divided by the GLM length of front 2D, and where length just gives you the magnitude. And just make sure that everything is in the parentheses there. And then now we want to rotate it, so we're going to say model is equal to GLM rotate model theta camera default camera dot camera up. Alright, so let's run this. Okay. So that doesn't look right. Although it does kind of look right. Because I'm moving the mouse right now, and that's kind of rotating properly. But once I get it past a certain threshold, it's going the opposite direction, and that threshold is actually where z becomes negative. Now the reason for this is, let's look at the xz plane right over here. The arc cosine, or the inverse cosine, can only return an angle in the first or second quadrants. So, and these are going to be positive angles, so plus. So if it turns out if z is negative, so in the first two quadrants z is positive, if z is negative, all we're going to want to do is just pass in the negative of the angle. Is that right? Yeah, I think that sounds right. Yeah. So what we're going to do is theta there. So if front 2D, or let's say if camera default camera dot camera front dot z is less than 0, we're going to pass in theta, or we're going to pass in negative theta. Otherwise, we're going to pass in theta. So let's run this and see what happens. Now, we are getting a problem because it's actually just rotating incorrectly for all angles now. And the reason why is because the angle of rotation is actually the opposite. So even though our cosine returns something here, around the up, it's gonna rotate that way. So we want to do, if z is negative, we want to return the positive theta, otherwise we want to return negative theta. So now let's look at this. Oh, and we got an error. Alright, so now this looks right. And there is a little bit of wobbling, which I'm not entirely sure how that's... What the heck? Okay, I think we're gonna have to fix something. But let's just do the second rotation now. So the second rotation is between the up and down vectors. So once again, we're gonna be getting the angle using a dot product, but now we're gonna be doing it between the camera front and the gun front. So we want to rotate it from the gun front all the way to the camera front. So this is going to be an angle in 3 dimensions now. And because we can't really determine gun front, we don't have that, it's going to become a problem. But what we do know is that we know camera up. Now the reason why we can use camera up instead is because camera up and gun front are always perpendicular to each other. Camera up, yeah, that just makes sense because camera up is 0, 1, 1, and the gun front is 1, 0, 0. So if you were to take the dot product, you would get a 0, and if the dot product of 2 vectors is 0, that means that they're orthogonal or perpendicular. So that's how that works. So we can just then offset the angle by pi over 2 radians. So let's do this. We're gonna go ahead and rotate it. Let's just do it down here. Alright, so now rotate around camera right using dot product. So we're gonna use theta again. So theta is equal to the arc cosine of the dot product of camera default camera dot camera up and camera default camera dot camera front, and now we need to divide it by the magnitudes of both camera up and camera front. So divide by, and we're going to say GLM length of camera default camera dot camera up, and then divide by GLM length of camera default camera dot camera front. I hope that works. Yeah, that seems right. And now we're going to say model is equal to GLM rotate model. And once again, we're going to offset it by pi over 2 radians. And then we have to negate it for the same reason that we did before, because it's just the rotation direction. So what we're going to say is, we can't really get a pi, or that's not really a constant. So we can just use actually the GLM function. So GLM radians 90.0f minus theta, and then camera default camera dot camera right. And once again, offset by pi divided by 2 radians, because angle between cam front and gun front. Alright, so hopefully there's no errors there, and let's go ahead and run this, and let's try and running this. Oh. This should not be happening. Let's try and reverse the order of the rotations. No, builder. Oh yeah. And just make sure you put the type definition for theta up in the first definition only. And it should be negative again. Even though I... Oh, this is not proper. This is not good at all. What the hell is going on? Hold on. I'm looking at this and it looks right. It might have something to do with the position. Okay, yeah, so... Oh, I know why. I know exactly why. Okay, so when we set position, we were doing something wrong. Because camera up is not the direction that we want to go in. Because camera up is the 1.0 direction. Let me just... Yeah. So it's a little weird, but the reason... so we're gonna have to recalculate... Or, you know, let's actually try this. So, in camera.cpp, let's try and reverse the cross product real quick. So, camera... front. No, that's gonna change a lot of things. Here, let's just... Oh, alright, let's just try this. Okay. So above where we set position, we're gonna want to recalculate a down vector. So glm vec3 down. And this time we're going to do an operation that gets the vector perpendicular to camera front and camera right. Now, the way we do that is we just take the cross product, and the cross product returns a vector, not a scalar. So we're going to say glm cross between camera, default camera.camera front, and camera, default camera.camera right. And then what we want to say is, instead of adding camera.camera up, we're going to say down times and then positive 3.15. So let's go ahead and look at this in the visualizer. So our default look vector, or default front camera, is 1, 0, 0. And our default right vector is 0, 0, 1. So let's draw that. So that just looks like that, where the red vector is going upwards. Now, we're going to go ahead and take the cross product, which in this visualizer we can just put here, and you see that it's in the negative y direction. And that's what it should be, so we're just going to retake the cross product. I'm hoping I'm doing this right. I feel like this should work. That's not right at all. Okay, there's something wrong with... Because as I go further out, the varyings about something get really strong. So let me try it. Here, let me just look at I'm gonna look at my code real quick. Alright, float theta is equal to the arc cosine of the dot product between camera up and camera front, divide by the length of camera up, divide by the length of camera front. Now, then rotate the model by, you know, let's try doing something different over here. Let's call this a tan of 1 times 2, which is an equivalent expression. Oh, a tan f. Nope, didn't change anything. And then rotate it around camera right. This is getting really weird. Alright, and then front 2D is the 2D vector of camera front X and camera front Z. Theta is equal to the arc cosine of the dot product between vec2 1.0 and front 2D divided by the length of front 2D. And then we just rotate front to... Let me try doing this actually. This might be the problem. GLM vec... Yeah, I think this is the problem. Yeah, okay, there we go. We're just getting... oh, you know, I know the reason why. So when we were rotating it horizontally, what we were doing is we weren't only doing it horizontally because camera up is not perfectly 0, 1, 0. I don't know why I tested it and it worked. I guess I have to look at that again. I can also change this back to camera default camera up, and we can just subtract that. Here, I'm actually going to write out why this works. This expression works in a second. So let's go ahead and run this just to make sure that works. Okay, so yeah, I just think I needed to negate the rotation here. So just theta minus a tan f1 of 1 times 2. And we looked at why this expression is equivalent to pi over 2 in the shunting yard algorithm video a week ago. Huh. No, it's still giving me the wrong rotation. Okay, there's something wrong here. Let me try replacing camera up with the world up vector, which is that again. Alright, so the horizontal rotation works properly, it's just this is in the negative direction. But I changed that. Alright, let's run this and hope it works. There we go, okay, now it works, perfect. Beautiful. Alright, so yeah, that's honestly perfectly aligned with the eyesight. And we also have our flashlight that works. So yeah, that is basically... Here, you know, let me change these vectors because I don't want to put the numbers there. I want to make the world up. Is world up even a thing? Yeah, world up is a thing. So make this camera, default camera dot world up, and the same thing up here. All right, perfect. So you see that I'm moving the mouse left and right, and it all works. So yeah, that's kind of the basics of an FPS game or program. you know, you have the, I mean, we could add more animations where the gun isn't perfectly in your eyesight, where it's like off to the side, and then when you right click, we can figure out how to do that, and that'll just be another translation and rotation. Yeah, and then that would be a little weird to do, but I'll test that out, see how it works. But yeah, so that is basically it for now. Okay, damn, this model is almost 50 megabytes. God damn. All right, whatever. So yeah, this is pretty cool. This is how pretty much FPS games works. They start with this rotation stuff, and remember, this translation stuff. I promised to explain it, and I will. Just varies based on the gun model. So if it's a pistol or something, the sights are going to be lower on the gun, so we wouldn't translate it down as much. So let's go ahead and look at this expression in OneNote one more time. So let me just get this. And I will make this. There we go. Okay. Alright, so the expression is, so camera position. So let's look at this. So let's say that our, let me get a 3D coordinate system to kind of map this out. And I want the y-axis up. Nope, none of them are giving me the y-axis up. Oh, this one is. Alright, yeah, I guess we can just use this one. That's fine. Alright, so let's say that our camera position is to P. So let me draw a vector to that, like that. So that is P. And let's say camera front is like that. So F is looking like that, and camera up is coming out of the page, and it looks something like that. So camera up is that, front is that, that's F. And I'm just putting the arrow above it for the vector notation. And like I said, these are both normalized. So the unit vector in these directions is just the vector. So F hat is equal to F. And U hat is equal to U because they are normalized. So let me actually just type that out. Alright, just like that. So when we actually go ahead and translate something, we're gonna, it's kind of like we're taking this and we're moving it 8 lengths down. So I'm just going to do 1, 2, 3, 4, ... So the model sits right here by default at 0, 0, because that's the initial position. And then we translate it upwards to the camera position, and then translate it forward in the camera forward direction to out here. And then we translate it down by 3.15 units. So that's just downward. So this way 8.0, and then downward 3.15 units. So that's how that works. It's just all a bunch of vector addition and subtraction. And because we have these components separately, these unit vectors can be exchanged for x, y, z, one along. So I'm not going to get too much into coordinate systems, but in essence, you can remake a coordinate system into whatever you want. So you can make a coordinates, like in physics when we do like incline problems, I remake my coordinate system so the x direction is there and the y direction is there. And let's say the object is moving up, so then the x unit vector I had is like that. So it's in the motion of the object. And essentially what we're doing is the exact same thing, just using a different axis. We're using several different axes here, where each axis is in terms of the x, y, and z axes, so we can translate them. It's like having a different reference frame. So yeah, that's I won't get too deep into it. It's probably not that interesting, but I enjoy looking into the math of it. It's pretty fun. So yeah, that's pretty much all I wanted to do today. It isn't that late, so I actually do want to play some games later tonight. So I'm probably gonna go back live in like 10 minutes. After I take a fat fucking shit, and then yeah. So next video, once again, don't know when it's gonna come out. We're gonna be working on moving the gun down, or like moving it into a separate position, and then when you right click it'll go in your eyesight, and then I'll probably find something else to write some code for. So yeah, that is pretty much it. I have nothing else to say, and yeah, I've said yeah 5 times now. Goodbye. I'll see you guys in 10 minutes if you're my 3 million viewers. If you're coming back in 10 minutes, I'll be there in 10 minutes. Yeah. Fuck me. That's all. Goodbye.